CS 259 review paper on topic Review of Multi-Core Processor presented by Snake Othari from Computer Science Department, San Jose State University. A multi-core processor is a circuit that has more than two processors or cores that can be used for parallel processing and multi-threading. Multi-core processors enable better computer performance and also consume lesser power. Since the processors are close to each other, the data transfer between them is also faster. The main power of a multi-core processor is that it divides the work and different cores work on these separate threads or processes to give better performance. The disadvantage of this is that the multi-core processor's true power is reliant on the software. Since their introduction in 1970, microprocessors have played a crucial role in the advancement of technology. At first, a single CPU core was used to manage the application. Performance improvements for single core computers were limited in scope. The reason for this is because the clock frequency rises, power dissipation also does. A CPU that runs a faster clock frequency can execute software more quickly. This is the approach to performance improvement that has been used the most frequently and broadly since 1985. Parallelism is the greatest way to keep performance and power consumption constant while using a lower frequency. Through parallelism, power density and power dissipation are reduced while the number of registers grows. As a result of this idea, multicore was developed. A multicore processor is an integrated circuit that has more than two processing cores connected to it in order to improve performance, reduce power consumption, and expedite the simultaneous processing of several tasks. Essentially, this implies that there are several processors on a single chip that share other system resources. The system bus and main memory are shared by all the CPUs. Each core has an own system cache. All of the computer's peripheral components are then linked to this bus, as seen in the diagram. There are different types of processors based on the number of cores. Processors having two cores are called dual cores, like Intel Core Duo. Processors having four cores are called quad core, like i3 9000D. Processors having six cores are called hexacore, like i7 8700K. Processors having 8 cores are called octa-core, which is i9 11900K. There are processors with more than 8 cores, but these are the most popular and commonly used ones. Additionally, core types might vary amongst processors. It is referred to be homogeneous if every core has the same exact configuration, and heterogeneous if not. By dividing a larger app into smaller pieces and running them concurrently may, may cause performance to be boosted. Due to the increased reusability and benefits of a very simple design, this is helpful. On a single chip, heterogeneous cores house many types, each of which dedicated to a certain application. The load of animation and graphics, for instance, can be transferred from a CPU to the GPU by having a GPU installed on the system. The complexity of heterogeneous system does not diminish their value. Both these approaches are applied by multi-core CPUs. Architecture. To improve performance, multi-core design embeds many CPUs and cache memories on a chip. The memory cache, memory interface, and off-chip input-output circuits are frequently shared by multi-core designs. When compared to many CPUs on a single motherboard, this lowers the overall transistor count and cost while providing certain synergistic advantages. The figure on the left shows the fundamental designs of the multi-core CPU. The CPU frequently stores data in the and L2, L1 and L2, which serve as fast memories. The CPU and L1 cache are near together. Off-chip L2 cache is slower than L1 but quicker than the main memory. Compared to L1 compared to L1, L2 is a much bigger cache. Due to the size difference between L1 and L2, Hit time for L1 cache would be shorter than for L2 cache. The average multi-core processor has an L1 cache that is 32 KB in size and an L2 cache that is 2 MB. The multi-core processor architecture may be separated into many categories, such as processing components and memory, based on comparable transits or features. If the data is not in the cache or main memory, the system must extract it from an external source, which takes exponentially longer than reading from the memory system. The multi-core processor architecture may be separated into many categories, such as processing components and memory, based on comparable transits or features. So, there are different types of multi-core architectures. The kind of multi-core architecture, such as reduced instruction set computer or complex instruction set computer, depends on the type of instruction set architecture. The processing component employed in the core of a multi-core processor also affects its design. In order cores and out of order cores are two distinct types of cores based on the processing element. In order cores perform with ease in big applications with more sensitive serial sections and higher levels of parallelism because their small device footprints and low power consumption. Out of order cores take up more chip area and are inappropriate for systems that need to be power efficient. These cores, however, perform well for applications that need high output and performance, as well as a variety of behaviors. In order to improve the performance of multi-core processors, such as those such as those on the right side, it is preferred to use the single instruction, multiple data, and very long instruction word architectures, as shown below. Advantages and disadvantages of multi-core processors. So, multi-core processors, which gradually increase processing power with low latency, can provide very significant performance gains to multi-threaded software due to their close proximity. The signals don't deteriorate noticeably, allowing for transmission of more data in a given length of time without repeating the signal. Customers' relationship with man customers' relationship management with larger databases, corporate resource planning, e-commerce, and virtualization are just a few of the examples of applications that will benefit the most. Embedded systems, data web servers, or online shopping, signal processing, CAD CAM, image processing, networking, and graphics are a few of the major applications for multi core CPUs. Multi core processors use lesser space on circuit boards. These processors are more reliable. Since multi core processors are located on the same chip, it speeds up the PC. It can work with more information as compared to a single core processor. There are several disadvantages of multi-core processors, such as when comparing a single core processor with a dual core processor, the speed of the speed is not typically double. These processors also require more power and face heating issue. It is more expensive as compared to a single core processor. The processor's performance is greatly dependent on the software running on it. Based on how well the parallelism is handled, we can expect the performance to vary. Parallel processor also involves uh, a lot of coding challenges, and hence the code for parallel processing is complex to write. So, improvements in performance as compared to a single core processor. Performance is measured as the number of instructions performed per second frequency. A task's performance is the amount of time needed to do it. This pertains to both the clock frequency and the quantity of instructions that are carried out each clock cycle. As a result, the performance may be computed as a function of the frequency and instructions per clock cycle. Although the multi-core processors individual cores might not be as fast as the most potent single core processor, the overall performance is improved by the fact that more jobs can be processed at once. Each program would receive a different time slice while utilizing a single core CPU to run several applications, while the other programs would receive different time slices. If one of the processes takes longer to complete than the other, all the other take processes start to lag behind. However, many jobs may be completed concurrently in parallel on a multi-core processor. Each work will be completed by a separate core in parallel, enhancing performance. So, there are various problems with the multi-core processor as well, like cache issue. Depending on the program, a multi-core CPU will utilize a certain amount of cache space. For applications where data reuse is more common, it is preferred to utilize a big cache. Although the cost will be higher, the performance will be higher as a result of increased cache size. Access times are also quicker when cache sizes are larger. The quantity of cache levels required is essentially determined by the distance from the main memory or the number of cycles needed to reach the main memory. The cache levels will be greater and access will be quicker as the number of cycles rises. Homogeneous and heterogeneous cores. The second problem that develops with the creation of multi-core CPUs is the use of homogeneous or heterogeneous cores. Every homogeneous core performs the same operation at the same speed with the same functions and cache sizes, but heterogeneous cores come in variety of frequencies, memory kinds, and capabilities. The choice will depend on how much customization and processing complexity can be traded off. Parallelism. To fully benefit from the multi-core processing technology, programs should be able to run in parallel, which leads us to the third problem. There are there are three different kinds of parallelism. A parallelism at the level of instructions, parallelism at the level of threads, and parallelism at the level of data. In the case of instruction level parallelism, the instructions may be executed sequentially or concurrently. In the instance of thread level parallelism, the processor is given many threads of the same job to be handled concurrently. Memory coherence allows data level parallelism to share common data among the processors that are already operating, increasing performance by reducing the amount of time needed to load and access memory. The fourth problem is speed and power. Today's applications need high performance, which calls for short processing times. A multi-core processor's performance can be increased by using many cores or by expanding the cache. In the event that the number of processing components is increased, the system will require more static and dynamic power. Overheating could, could potentially be a problem if every core performs to its fullest capability. Therefore, strategies or plans to achieve outstanding performance at a lower rate of power consumption should be employed. Challenges. Energy reduction. To boost multi-core performance, several cores are arranged on a single die. This system uses more energy as a result. To achieve this, it is necessary to run the tasks on the cores using some sort of power saving method, allowing the system to operate at higher speeds and throughput while consuming lesser power. The cores may be run at lower frequency, or the unused cores may be turned off as part of these strategies. Multi core systems face challenges with load balancing between cores and reducing power consumption. In order to address these issues, numerous authors have presented a variety of study findings. The battery backup time can be increased while achieving energy optimization through the use of dynamic voltage scaling or DVS approach. It increases the likelihood that the deadline will be missed or the response time will be prolonged because this method forces the processor to operate at a lower voltage level with longer computation time. In these circumstances, in order to meet deadlines, the tasks are created to operate at high voltages or rapid speeds so that the system's power consumption can be reduced. The appropriate speed should be selected. Power and temperature. Theoretically, if two cores were added to the processor without any changes, it would consume twice as much power and generate twice as much heat. In the worst instance, the computer could potentially catch fire if a processor overheats. Each design accounts for this and reduces the frequency of multiple cores to conserve power. Many designs also feature a power control unit, which can reduce the electricity output or turn off unused cores in order to reduce excessive power consumption. This chip, the chip is designed so that the hot areas does not expand much, that the heat is distributed evenly throughout the chip to reduce the heat produced by multiple cores. Memory consistency. The latency on large scale shared memory must be reduced in a multi-core processor environment, and memory consistency is essential. The actual memory required for pipelining and buffering to lower memory access latency depends on the processor's architecture. There have been a number of models for memory consistency proposed, ranging from the sequential consistency model, which is the strictest model, to the release consistency model, which is less strict model. Buffering and pipelining are restricted under the sequential model, which employs the interleaving execution concept. Memory access can overlap thanks to the release consistency model. Between the release model and sequential model, there are other models as well. When compared to the sequential model, the findings of various models showed that less rigid models are more beneficial in multi-core processor architecture. Cache coherence. Cache coherence is, is an issue in a multi-core scenario due to dispersed L1 and L2 cache. Since each core has its own cache, the copy of the data in the cache might not always be the current version. A dual core CPU with memory block brought into each core's individual private cache is an example. Unless its cache entry is invalidated and a cache miss occurs when it tries to read that value from its cache, the second core won't have the updated copy when one core writes a value to a specific location. This cache miss necessitates changing the second core's cache entry. If this coherency policy wasn't in place, trash data would be read and incorrect results would be produced, which could cause a program or the entire computer to crash. A directory based protocol and a snooping protocol are the two main approaches for cache coherence. Only bus based systems are permitted to utilize the snooping protocol, which uses a number of states to determine whether or not it needs to update cache entries, and if it has control over writing to the block. The directory based protocol is scalable to numerous processors or cores and can be used on any network, in contrast to espionage, which is not. In this approach, information about which memory regions are used exclusively by a single core cache and which are accessed simultaneously by numerous caches is kept in directory. The directory is aware of the need to modify or invalidate a cache block. So, in conclusion, this paper explains the core idea behind multi core processors. It lays out the architecture of the multi-core processor and an overview of the types of multi-core architecture. The presentation also talks about the need to move towards multi-core architecture due to the single core's power limitations at high clock rates. Multi-core technology has become feasible and is the current industry trend. However, in order to properly utilize multi-core technology, certain issues and challenges are also brought about by increasing the number of cores and must be carefully addressed. The fundamental challenge for multi-core processing is the rising demand of powerful computation while consuming less battery power. A multi-core's energy usage can be decreased by using DVS schemes, idle slot accumulation, or activating sleep state of the cores. As energy usage declines, system performance will rise. Thank you.